Hello everyone. Let us start with constant head test. As I have told you in the previous video, there are two tests which are used to determine the permeability. So first one is the constant head test and second one is the falling head test. So in the constant head test, let us first draw a diagram. Okay, and then I will tell you the test in details. So just follow me and you copy down the diagram. First one is the it is a setup in which first one uh, there is a source of water. Okay, the water will start falling from here. There is a source of water here. Okay, then the water will be controlled using the like you can say the nozzles here. The flow of water can be controlled by using the nozzles here. Then here is a cylinder. Okay, and in the cylinder we keep a soil sample. In this cylinder we keep a soil sample. Okay, and the soil sample's cross sectional area will be defined. Okay, the soil samples cross sectional area will be defined. So this is the soil sample. Okay, so the cross sectional area will be defined for the soil sample because the cylinder is will be having constant dimensions. Therefore, the cross sectional area of the soil sample will also be same. Okay, then next one is since the water is falling, so if we keep two manometers here, we keep two manometers. First manometer we keep here and the next manometer we keep here. So manometers are used to find out the heads. Okay, so at this point, one second. At this point, suppose the head of water is seen that it is here. Suppose the head of water is here, and at this point, when we check for this point, the head of water is shown here. Okay, so when we look at this point we see that the head of water is here, and when we look at this point we see that the head of water is here. So the difference between the two will be this one, isn't it? The difference between the two will be this one, and uh, difference between these 2 points where we are measuring the heads, let us consider it as L. L is the point between which we are L is the length, or we can say the distance between the points where we are measuring the heads. Okay, so first this point in the soil sample, and next is this point in the soil sample. So 2 points, we are getting two heads, this one, and for the next one we get this one, so difference of head we get. Okay, and length between difference between the 2 points we get, the length, the gap between the 2 points is L. Okay, and then the remaining water after passing through the soil sample, it is then collected separately. Okay, the remaining water, it is then collected separately. So now if I try to find out the equation, or you can say the permeability, first we have to start the test by pouring water from here. You have to start pouring water. At one point of time, what happens is, when we keep on pouring water, this level of water, this head that we get, it varies for a certain point of time. These two levels, it varies for a certain point of time until the point when it becomes constant. That means now the head becomes constant. For the first, from the starting, the head varies a little bit. H varies for a certain time, and after a certain point of time, the difference between the two levels, these two levels, becomes constant. Okay, and at that point of time, we have to note down what is H. Okay, then Q also we can find out, because we are actually determining the we are actually controlling the flow, isn't it? Q we can find out because the flow will be controlled by us. So ultimately, if we use these values into the equation, how will it look like? So let us see the equation. Q is equal to KIA, we know. So A is the area of cross section which we get from the soil sample. Okay, so A is the area of cross section we get from the soil sample. It will be the nothing but the cross section of the cylinder, because the soil is placed inside the cylinder. Now if I write it like this, K is equal to Q by IA, isn't it? So I we can write is what? H by L, isn't it? Difference of head by the distance between them. So uh, let me find out some space here. So K is equal to, we can write Q H by L A is equal to Q L by H A. K is equal to Q L by H A, you can write, isn't it? Now let me take a new screen. So K is equal to Q L by H A, isn't it? Now Q is the flow, isn't it? Flow per unit time. So uh, amount of flow, total flow, if we can measure the time. Okay, suppose we have done the experiment for a amount of time t. We have done the experiment for a particular amount of time t. Suppose this experiment. Isn't it? This was the soil sample. This from here the water is poured, isn't it? So for a time t, for a period of time t, when the experiment is done, the water is collected here, right? Amount of water collected here is this one, right? So I can measure the amount of water collected, isn't it? So suppose the discharge collected is q. Amount of water collected is, or you can say amount of discharge collected is q. So small q will be what? The discharge per unit time. Q is nothing but the discharge collected. Okay, so finally, how will the equation get modified? So K is equal to QL by AH. It's already there, isn't it? So in place of Q, I will write Q by T, L by AH, or we can write QL by HAT. So this is the time of like experiment actually. Amount of time t is the time interval in which the experiment is done. Okay, so ultimately in this way we can find out k. So this is how the constant head test is done. Okay, so next let us go to the falling head test. So in the falling head test, the diagram is pretty simple compared to the constant head test. So you should uh, you should understand that I will not be able to draw it perfectly as it is in the book, isn't it? As compared to that in the book. So I recommend that you please go through the diagrams in your book. Okay. Using a graphic tablet and a graphic tablet pen, it's very difficult to draw it as accurately as it is in the book. So I recommend please you go through the books. Okay, and I have tried to draw it as simple as I could. Okay, so that you can understand it. Now in this falling head test, what happens is, so this is the way through is the water will enter the soil sample. So this is the soil sample. This is the soil sample. So it will have a cross sectional area A. Okay, now what will happen is this one is the pipe, isn't it? And length of the sample is this one, L, and this pipe will also have a cross sectional area. Okay, this pipe will have a cross sectional area which will be taken as small a because it is small. Okay, now at the very beginning when the water will start falling, the at first assume that the water is here. Okay, and this is the bottommost part. This is the bottommost part. So assume that at first the water is here. So first the head is this one, each one. Now assume that at after a certain point of time, the when the water is falling down, the water is, suppose after a point of time which is after a passing of t amount of time, t seconds, the water is here, suppose. Okay, so now the second head is H2. So in a duration of T, the head changed from H1 to H2 when it was falling through the soil sample. Okay, so that is the thing that we require. Okay, remaining things are area of the soil sample, area of the pipe, area of the pipe, length of the soil sample we already know. Okay, so what will be the equation? The equation for permeability is, for the falling head test, this one. Okay, so I hope you have understood this experiment. It is very simple. Now, when you encounter soils having various layers, suppose, let me give you an example. If you are encountering soil having various layers, so these soils will be called as stratified soil. Stratified soil. So let us take for example a soil having this much amount of layers, and the thickness of the layers are, suppose, H1, H2, H3, H4, and the permeability of each layer is, suppose, K1, K2, K3, and K4, and uh, suppose the water is flowing in this direction. Okay, then in that case the flow is what? Flow is normal to the planes, isn't it? The flow is normal to the planes at 90 degree to the planes. So that in the equivalent permeability of the sample will be termed as Kv. Okay, when the flow is normal to the planes, the equivalent permeability will be this one. H is nothing but the total thickness. So this is when the flow is normal to the planes. Now there will be another situation when the flow is parallel to the planes. Okay, the flow will be parallel to the planes. Then in that case, the equivalent permeability of the sample will be called as KH. KH. And KH will be equal to 1 by H into K1 H1 plus K2 H2 plus K3 H3 plus K4 H4. So this will be when the flow is parallel to the bedding plates. Okay, the flow is parallel. So two types of permeability we have encountered. Equivalent permeability, like we find out the equivalent stiffness of springs or equivalent discharge, okay, or equivalent voltage, all those things. Similar concept. We have to find the equivalent permeability for two situations: when the flow is normal to the planes and when the flow is parallel to the planes. Normal to the planes we have already discussed, and this is the formula for the flow when it is parallel to the plates.